Welcome back. Multi-user MIMO is an extension of standard MIMO. So recall in standard MIMO we had our transmitter with multiple antennas, our receiver with multiple antennas, and then maybe our transmitter and receiver did some pre-coding and combining using SVDs, and we had our channel. Now we will have possibly multiple receivers, each with their own channel, receiver 1, receiver 2, or we will have a case with multiple transmitters and a single receiver, each with their own channel. Okay, so we have this case with multiple receivers, or this case with multiple transmitters. And typically, on one side there's only one device, on the other side there's multiple, so this will be the base station, and this will be the users. And this will be the base station, and this will be the users. So this is the multi-user MIMO scenario. Now, why is this important? To understand why this is important, it's good to revisit our multiple access slide. So you recall that in multiple access, we wanted to create dedicated channels for each of the users. We saw FDMA, TDMA, and CDMA. In FDMA, each user got its own frequency band, and they were non-overlapping, so all the users were orthogonal. In TDMA, all the users got to use the whole frequency band but use different time slots, and that way they remain orthogonal. In CDMA, all the users could use the same time and frequency, but use the code. And that way they remained orthogonal, but this came at a cost in terms of rate, right? Because each user needs to send a sequence of symbols for each data symbol to transmit. But there's a dimension here which is now missing, which is called space division multiple access. So to use space to divide different users. So this means that different users could transmit at the same frequency, at the same time, using the full available resources, but then are divided through space. This is what we will see in the multi-user MIMO part next. So multi-user MIMO was originally come up with in order to create rich channels. And this is because when you have standard MIMO, typically your channel rank will be quite low. So even though you have many antennas, you're limited by the environment geometry, and you will have just a few large singular values, and all the rest will be zero. So this, if I draw this, I want to minimum, let me zoom in. Okay, so minimum MRMT, that's the maximum rank of the channel. And what would happen is that you would just have one large singular value, and then it would quickly decay and it would go to zero. And adding more antennas, well, it didn't help you in any way. It would just create more zeros here. So that's why in standard MIMO, you cannot really benefit from high rank. You will never create very rich channels. In multi-user MIMO, you create rich channels because users are spatially separated, right? And that's what this picture shows here. So on the left, I have the base station. On the right are the different users served by this base station. And they are in different places. So you can imagine that around each user, there's a ring of scatterers, and these rings are different and have different shapes. And this will lead to very different channels per user. So even though each user may have a relatively low rank channel, so each user's channel in terms of the, well, these are actually sigma II, sigma II. Each of them has a low rank channel. The combined channel seen by the base station of all of the users together can have very high rank. What does this look like mathematically? We consider separately the uplink and the downlink. In the downlink, signals are sent from the base station to all of the users. The signal sent by the base station, let me write that first, is X, which is the superposition of the signals for all of the users. Okay, so xk for user k. And this may look a bit strange, right? Because you don't separate users anymore in time and frequency. You just send all of their signals together, overlapped. What user k then sees is its own observation, which is this transmitted signal passed through its own channel, right? So, and I can decompose this into the signal intended for user k and the signals intended for the other users. And I would really like this to be 0. So, like this to be 0. And we will see later how this is done. So now user k should take this observation and recover its own data, and this is an inter-user interference or multi-user interference. In the uplink, each of the users sends its own data. So this is sent by user k. This data goes over the user kth channel, right? And now note here that I put a transposed, and this is because when the channel from the base station to the user is H1, the channel in the opposite direction will be H1 transposed. And then the base station receives the superposition of all of the signals from all of the users, and this is its observation, and then it needs to recover each of these signals. In this lecture, we'll always assume channel reciprocity, so time division duplexing. Okay, this allows us to write this relationship here. So let me just highlight this. Channel reciprocity. This allows us to write the channel in uplink and downlink. So in downlink it's H1, in uplink it's H1 transposed. Now the uplink case is actually not very hard. I can write this sum out in this product of these two matrices. Right, so this here is a MR by 1 observation. And I can just write it out as this. So it's H1 transposed X1 plus H2 transposed X2. And by just computing this product, you obtain this sum plus noise. And now I've basically created a system where I have Y is H, X plus N. Right? It's just now this X contains the signals of all of the users. And this H contains the channels of all of the users. And this H here is now MR by KMT. And as long now as I make MR sufficiently large, so larger or equal than KMT, I have a good chance of recovering the data of all of the users. So if each user has 2 antennas and there are 10 users, I would like 20 antennas at my base station. So let me write this down. MT is equal to 2 per user. K is equal to 10 users. This would imply that MR is equal to or greater or equal to than 20 at the base station. Because that is needed, for instance, to do zero forcing detection. Now the downlink is a bit more tricky, right? Because again, the signal at the user has this multi-user interference, and user K is not interested in this signal. We really want to make this 0. So if the base station does not know the channel, then there's not much to do. But there's no way for the base station to help the users avoid the interference. So the only thing it can do is to send to different users in different time slots. So this means we can do TDMA, FDMA, or CDMA. But if the base station knows the channel, it can do something called multi-user precoding. And then it can send the signal to all of the users at the same time. And I put this happy face here because that means the rate will go up a lot. You can imagine if you have 20 users to serve and you serve them separately, one after the other, versus all at the same time, you will get 20 times more rate by doing this technique with the channel state information. So how do we do this? As you can imagine, we again do something like with SVD. So this is our observation as before. XK is a signal sent to the kth user, HK is the kth user's channel. But instead of sending this signal, we will actually send a modified signal. So we send WSK, where now SK is the data. And by then choosing these WKs, we saw them also here, we've now expressed our model as follows, right? So our observation is the channel, a precoder matrix. This is called precoder. This is also a precoder. And now we can design these precoders WK such that HK WK prime is equal to 0 when K is different from K prime. So that's really what we want to do. And if we are able to do that, that means that this would imply that the multi-user interference is equal to 0. So then the user K does not need to worry about this term, and this will go away. To understand this, how this is done, it's instructive to look at a single antenna case per user. So a base station has many antennas. Base station has a lot of antennas, and then there are a bunch of single antenna users, each with their own channel. So the kth user, there will be a downlink channel, which is denoted by HK transposed. And of course, then the uplink channel will be HK. Recall that the downlink channel is a row vector. Okay? Uplink channel is a column vector. That's why I put this transposed. So with this in mind, what will then be the signal seen by the kth user? The user has only one antenna, so it just observes a scalar. It will be the kth user's channel, AK transposed, times its precoder. Okay, and now the precoder will be a vector times the signal for that user. And then in addition, you have the kth user's channel, and then the precoded signals for all of the users. I can then stack the observations of all of the users together. Okay, this creates a vector Y. And of course, this cannot be done in practice, but this is just for me to show you how to design W. If I stack all of the observations together, I can write it in this form. So by stacking all the transmitted symbols for each of the users, all of the precoding vectors and all of the channels, plus noise. So this is observations of all of the users, is given by this H matrix, this W matrix, and the transmitted data. And now the question is how to design W. So how can we choose a W that makes sure that this constraint is met? And here we could do this using any performance criterion, such as zero forcing. So we want W, for instance, that H times W is equal to an identity matrix. And now it depends on the size of all these matrices. So let's try to do this exercise. If there are K users, this is K by 1. H will be K by the number of transmit antennas. And this will be MT by K. And we will now assume that K is much less than the number of transmit antennas, that we have enough transmit antennas available to solve this problem. So that means that W is a very tall matrix, so then we can solve for W as being the pseudo-inverse of H. Now I'm a bit hesitant to write it. Okay. So H Hermitian, H Hermitian inverse. To check how, if pseudo inverse is correct, you can always look at the dimension. So h is k by mt. No, then this doesn't make sense. Okay, I will undo this. We can look at the solution on the next slide. So let's take a break and then we come back with the next part.